In section 4.6, we're going to take some stuff we've done earlier, actually, but we're going to take our derivatives and use them to do some approximations for things that are a little bit tricky to do by hand. Again, a lot of this is not necessary these days because of the type of calculators we had, but just 50 years ago, it would be kind of a pain to try to figure out what the cube root of 75 was. And so we can use derivatives to help us do some approximations if you forgot your calculator, it broke or something like that. But I guess let's kind of play along and see how this works. So the first thing that we're going to talk about here is what's called linear approximation. And this is really nothing more than something that we've talked about previously. It really does not matter what sort of curve you have here, but if I'm looking at a very specific area, so I have to have a point that I have in mind to be able to estimate. If I'm, say, looking at this point right here, if I zoom in far enough here, so here's my zoom, but if you zoom in far enough here and take a look at what's going on, it's going to look like a straight line. And we've talked about this before. That was our first kind of description of what the tangent line is. So the idea is that as long as we're looking at a small distance away from some starting point here, we can approximate any curve. Doesn't have to be a nice curve like this. It could be any curve at all with its tangent line. And we already know what the tangent line looks like. The tangent line is always y is equal to the slope, which is the derivative of the function, times x minus the x value of your point, plus the y value. Okay. So all we're doing in section 4.6 is really kind of fancying it up and giving you some different wording and a slightly different notation here. Excuse me. First of all, the textbook likes to give the linear approximation a name. I should write this out. So the linear approximation of f at x equals a. So I want to pause here. I started to give a definition, but I want to make sure it's clear. You have to have two things at the beginning to do your estimate. You have to have a function that relates to what you're trying to estimate, and you have to have a value that's easy to work with, that's very close to the value you're trying to work with in your approximation. Okay, but the linear approximation, our textbook uses L of x to show that it's the linear approximation. I guess I should say, first of all, that f of x is about the same thing as the linear approximation, which is going to be the derivative evaluated at a times x minus the x value of the point is a. And the y value, you always, again, get the y value by evaluating the function at the x value. So really all that's going on here is we're rewriting this, so all you need to know is the x value. You don't have to worry about finding anything. I shouldn't say finding y. You have to find y as part of the process. We just kind of hide it there. You don't have to worry about x naught and y naught here. If you know where you're looking for your approximation, it's just a matter of finding the derivative, evaluating to get the slope, evaluating the function to get the y value, and then plugging everything in. Okay, so let's just start with this. We won't actually estimate here. Let's say that we're asked to find the linear approximation of f of x is equal to x over x plus 3 when a is equal to 3. Okay, and sometimes it'll be written like that. That's how our textbook starts. You can also kind of cross this out lightly and just say near x equals 3. That's another way that it's going to be worded. But whether it's giving you an a value or it's saying, hey, we want to be somewhere close to this x value, either one, that's the value that you're going to be evaluating your expression at. And so this is, once again, nothing more than make sure that you're extra confident when you're finding the derivative. To find the derivative, we have the quotient rule over there. Derivative of x is 1 times the denominator, minus the derivative of the denominator is also 1 times the numerator. and that's all over the denominator squared. And there's certainly some simplifying to do here. You don't have to, because we know that we're going to be plugging 3 in. So if you want to just plug the 3 in now, you can. But notice that 1x minus x will end up canceling out. So you're just left with 3 over x plus 3 squared. And so now that we know that, we evaluate at 3 to figure out what our slope's going to be. So I throw 3 in here. 3 plus 3 is 6. 6 squared is 36. 3 over 36 is going to reduce down to 1/12. Okay. So that's where all of our work comes into play. And we're not finished because we have to fill in the blanks here. So we're done with our derivative. We already know what a is to plug in there, so that's not a big deal. The only thing we have left is plugging the 3 into the original function. So if I go into the original function here, where did I put it? It's right there. We've got 3 over 3 plus 3. Well, that's 3 over 6, which is going to reduce down to 1/2. Okay, so now it's just a matter of plugging this in, and I don't quite want, I'll just move this down a little bit for now. So putting it all together, we know that the linear approximation, L of x, is going to be the slope, or the derivative, evaluated at 3, which was 1/12, times x minus the value of a there was given to us as 3. And then we have to add on the function value, which we just found to be 1/2. Okay. And as always, it's best to go ahead and simplify this so that it's not as hard to work with later on if you're going to work with this for a handful of different ways. But if you distribute the 1/12, you get 1/12x. Distribute here, the 3 and the 12 will cancel down to a 4, so this is minus 1/4. Negative 1/4 plus 1/2 is positive 1/4. So if you're just looking for the linear approximation but not actually estimating a value, that's it. Okay, so it's in a different format here, but just to reiterate, this is nothing more than the tangent line. It's just giving us a nice kind of different viewpoint in terms of how to write all of that out. So just mark that one more time. If you like to find the tangent line some other way, or you do it in a different order, some other similar process, do whatever you want to do there, but the linear approximation is nothing more than the tangent line. And so I'm not overly concerned about that type of example because in general, as long as you know that the linear approximation is a tangent line, it seems like we've done that enough that we're getting comfortable with that idea regardless. What's a little bit trickier is going through and using that to estimate some values that might not quite be as clear of what you need to do. So say we're asked to use an appropriate linear approximation to estimate the value of the cube root of 65. Okay. So at the beginning here, what makes this a little bit tricky is you have to make two decisions. One's not really a decision, but it takes just a tiny bit to kind of look at it, make sure that we're clear about what's going on. But you have to find the function that's related to the expression. And most of the time, this is not too bad. Sometimes it's a little trickier than others just because of the way that the textbook writes things. I'm not overly worried about that. But in this particular case, if you're taking the cube root of a number, the function we're looking at is just the cube root function. I could have made it a little bit more interesting, I guess, by giving you something other than a cube root. I didn't want to do anything overly complicated, though. So all we're doing is saying, well, the thing that's happening to 65 is we're taking the cube root of it, so we better be examining what happens with the cube root function. Okay, the second part is to choose. This is actually your choice. You can make a lot of different choices here that if you had a calculator would work, but kind of remember, the idea is that, excuse me, we're trying not to use a calculator here. So once I have this function chosen or found, we need to choose a value x equals a. So that's the same as before. That is easy to work with. And is near, in this case, 65. And remember, a is representing an x value. 65 is an x value of the function that we're looking at. So what we're really doing here is saying it doesn't have to be super close. We don't have to be working with 64.95 or 65.0001, anything like that. We want to be relatively close, but we want to pick something that's going to be easy to work with regarding this function. Okay, so I have a feeling you probably have a decent idea right now what we could be plugging in. If you're ever unsure, just wait for a split second. Take the derivative, because remember, you're going to have to be working with that derivative as well. And once you see the derivative and the function together, you might be able to say, oh, I want to use this number. So let's just go ahead and wait on this for just a split second. Take the derivative of the function. Just a reminder, maybe some of you have done enough of these examples that you have a faster way of doing this, but I would always write that as a rational exponent because it doesn't come up enough to memorize the derivative. And when you take the derivative, then you are multiplying by the exponent and decreasing the exponent by 1, which looks scary, but we've seen this in some other examples where x to the negative 2/3, the negative would just put you in the denominator of the fraction, and x raised to 2/3 is nothing more than the cube root of x squared. Okay. So at the end of the day, what it boils down to is, like I said earlier, I think it's probably obvious from here, but in both cases, we need to be able to take the cube root of whatever we're plugging in here. Okay, so we want to make our linear approximation use a value x equals 64 because the cube root of 64 works out to be a nice integer. Okay, so we're going to use a equals 64, not because it specifically is the cube root is 4, but the fact that it is working out to be a nice whole number integer that we don't need a calculator for. Okay, so really at this point, forget about that guy. We're really just creating our linear approximation using this information over here. And when we finish, we'll just plug in the 65. Okay, so there's only 2 things left to do here. We have to find the derivative and evaluate, well, not find the derivative, but take the derivative and evaluate it at 64. And I should be a little bit careful here. I probably wrote that in a bad order for us. Remember, the order of the root and the exponent don't matter. That's something from algebra. So you can look at this as the cube root of 64 first, that we have to square. The cube root of 64 we said was 4. 4 squared is 16. So we've got 1/3 times 1/16. We multiply that across to get 1/48. Okay, so that's going to be the slope of our linear approximation. The y value is going to be whatever you get when you evaluate the function at 64. Well, that's easy enough. We just got done talking through that. That's just going to be 4. Okay, so putting it again all together with our linear approximation, you're getting that the linear approximation is the slope is 148 times x minus the x value. Sorry, it's right there, all over the place here. But I shouldn't have said x value, the value of a. Right? We're not ready to work with here. We're working with the 64 and all that. So this is x minus 64. And then we have to add on the function value or the y value. Okay, so honestly, we haven't done anything different yet than what we did before, other than realize we had to create our own function, choose our own value to be working with here. But now to do the approximation, it's just a matter of throwing 65 in there. So there's no need to necessarily reduce all of this because it goes pretty quickly, right? 65 minus 64 is just 1. So we have 148 plus 4. And this just depends on how you want to write an answer out. If you want to write a mixed number, that's not necessarily wrong. If you divide that out, you'll get about 4.02. Okay, so the moral of the story is, again, that's not necessarily perfect. You can use your calculator to take the cube root and see it's going to be I think it's 4.021. So it's really pretty close. But that's the idea. If you don't have a calculator to actually be able to compute the cube root of 65, you can get really, really close by using a linear approximation and thinking smartly about getting a number that's close to it. I'll just throw this out here because maybe some of you are thinking about this. But if I asked you to take something like the cube root, I think I said the cube root of 78 at the beginning of the video. 78, excuse me, is not particularly close to a perfect cube. Right? If we're working with 78, we'd have to be choosing 64 or 125 as the next perfect cube. It's right in the middle, so we can still kind of sort of get close, but it's going to be quite a bit further off than when we're working with something that's pretty close to an actual, in this case, perfect cube. And so, again, that's the idea of estimating using linear approximations. The only difference in the process is what function you're actually working with, but that should lead you through any of the different problems that you run into regarding linear approximation. Right, so the other thing that we need to talk about here is, for right now, also used to work with some estimates. But differentials become more and more important as we finish the semester up. They're actually kind of used in Chapter 5 in the background without talking about them in too much detail. Okay, so we're just going to start with some definitions and some notation that you've probably seen before, but change of x is the change in, the value of x. Change of y is, I forgot my equal sign, is the change in y. But this one we can add in a little bit more. It's equal to the change in y, but y is the function value. So this is really the change, like I said, in the function value, or f of x, if you want to write it that way. Okay, so I know you've probably seen this notation before. Change of x is no big deal because when we're working with these functions, we're the ones changing x, or maybe we're not changing x, but we can see how x changes. Our goal is to figure out, well, what is the change in x? What effect does that have on the function, or how does the y value change? And that is a really kind of tricky thing to be able to calculate depending on the complexity of your equation. And you don't want to have to sit down here and say, well, when x was equal to 2, you plug it in, you got this value. When x is equal to 2.15, you plug it in, you get that value. You know, especially that 2.15, depending on the equation, it could be kind of nasty to work with. And this goes back even further. I don't even want to talk about calculators here. There was actually two different mathematicians working with inventing calculus at the same time. One was concentrating on just kind of the idea of rate of change in the slope of the curve and the graph and all that. That would be, Newton. And then, excuse me, the other guy was really, I believe it was Leibniz, but I always forget that name. But the other person was really just concentrating on this. It wasn't so much graphing. It was, trying to figure out what's the change in the function value. So what he did was use what's called differentials that almost mimic the same idea of the changes there, but just a little bit different. And so dx, the d stands for the differential of x, is still the change in x. It's just different notation. So there's no difference whatsoever between change of x and dx. In general, if you want to say a difference, the change can be anything. If we're talking about dx, we're usually talking about minuscule changes. We're not talking about a change of 1 or 2. We're talking about a change of 10 to the negative 13th power or something like that. Okay, dy. I'm not even going to say change in y here because I want to make sure it's clear that it's really not the change in y. This is the change in the tangent line So, excuse me. So really the difference here is that we're going from taking the change of y, being really talking about the change in the actual function itself, whereas the differential y is the same thing as the change in the tangent line. Again, our textbook's not going to say the change in the tangent line. It's going to be the change in the linear approximation, which is the exact same thing as the tangent line, just a little bit more formal. Okay. And the idea is that it's super easy to figure out. Because the linear approximation is just a line, you can figure out how much the line changes based on the change of x just by using the slope. You don't have to have any sort of extra information here. Okay, so what's going on is we can use, again, these differentials to kind of estimate how much the function is changing without actually coming through and having to deal with some function values. Okay, so let's leave that over here and get rid of this, because we're not actually going to be finding any changes in y. We're going to be focusing on the differentials. Okay, so let's take this one step further. If these are our definitions, then the slope of the linear approximation is just same thing as always. It's the change in y divided by the change in x. So this is dy dx. And just taking a step back, remember, this is one of our different notations for the derivative. And that's where it actually comes from, is that dy and dx just stand for change in x, change in y. The slope of a line is just this. The slope of the line, again, because this is the linear approximation of the function, this really, maybe I should be clear, this is the linear approximation of f. But the slope of the linear approximation of f, that is absolutely positively the derivative evaluated at whatever x value you're looking at is going to be dy divided by dx. Okay. So I know it seems like right now all I've done is say, well, the two notations are the same. But if you realize that in certain contexts, at least, that is not notation, these are actual values, then you can do just a little bit of algebra here, multiply both sides by dx, and you find that the differential y is always equal to the derivative of the function evaluated at the x value that you're dealing with times the change in x. Okay, and that is the relationship that we absolutely need to have in the back of our mind. We're going to use it once to do an estimate here, but going down the road later on, we're going to see why it's somewhat important to keep track of what this is, because we're going to have to do some things with antiderivatives and changing some expressions around using substitution. This will really help if you keep this formula in mind. Okay, so the last thing to mention is notice that the change in the linear approximation depends both on how far you're moving your x value and the derivative of the original x value. There's kind of two different dependencies here. And I guess now that I've emphasized this enough, make sure that we're clear here that the idea is that the change of y should be pretty close to the differential of y. And as long as we're not moving a whole lot, the change in function value should be very close to the change in the actual, in the linear approximation. Right, so here, we're not going to be doing much at all. Just one example is showing this relationship, but as long as you know this is really the key thing to know about differentials. Not too concerned about being able to estimate. It's more for later down the road. But get my example back here. Let's say that we're estimating the change in the function f of x is equal to sine of pi over 2 times x minus pi over 3 as x increases from 1 to 1.1. So as I said earlier, this is still not a tiny change mathematically. So this is not going to be 100% accurate, but we definitely don't want to be trying to use differentials to say, well, how much does a change as x goes from 1 to say 50? that's not going to work. As long as I stay relatively close, we should get a relatively good estimate here. Right, so all we're doing here is this. If we can figure out what the derivative is evaluated at x and what the differential of x is, we're in great shape. So kind of taking this in order, first thing we need to know before we deal with either derivative or this is just what is x in this particular case. Okay, so I should be a little bit careful here. This is absolutely a relationship that we're going to use, and we don't always replace x with a number. But if you are going to replace x with a number, it's just this one. Right? That would be f prime of whatever value you're working with times dx. That is always a variable every single time. Okay, so the reason I'm writing x equals a number is because I want to make sure that we're clear what value goes in here. Does the 1 go in there, or does the 1.1 go in there? And it's always the initial value. You're always putting in the starting points and seeing how that changes. Right? If we're changing from 1 to 1.1, I need to start with the 1 in here. So the x value we're dealing with is 1. dx is the change between the original x value to the final x value. So the change from 1 to 1.1, you can subtract and write that out if you want, but that's just a change of 0.1. And so now it's just a matter of figuring out what the derivative of the function is and evaluate that function at 1. And we just figured out that x was 1, so we're going to evaluate it at 1 in a second. Right, so just watch your chain rule this time. So the derivative, the outer function is the outer function is sine. The derivative of sine is cosine. We're just dealing with the sine, so don't touch the inner portion of this right now. So it's still cosine of pi over 2x minus pi over 3. But then we do have to take the derivative of the inside still. So you take a look. I guess I could point here to the exact same expression, but the derivative of pi over 2x is just pi over 2. The derivative of pi over 3 is going to go to 0 since it's just a constant. So we just have it times pi over 2 out here. Okay. And then finally, if you're evaluating at 1, we just have to replace the x with 1. So pi over 2 times 1 is pi over 2 minus pi over 3. All that times pi over 2. Pi over 2 minus pi over 3, get a common denominator, so multiply by 3 to get a 6, multiply this by 2 to get a 6. You do your subtraction, you're going to be left with cosine of pi over 6 times pi over 2. And then finally, cosine of pi over 6 from, hopefully you have this memorized, but cosine of pi over 6 is square root of 3 over 2. And we're still multiplying that times pi over 4. Okay. So finally, we have to put it all together. So the differential y is equal to, excuse me, this value f prime of 1 that we just found. So it's the square root of 3 over 2 times pi over 4. And then we also have to multiply it by dx, which we found to be 0.1. Okay. And that ends up being, check my notes here, about 0.136. So that's what we're using to estimate. But notice it doesn't ask us to estimate dy, it's asking us to estimate the change in the function. So one last time, the change in the function is about the same as the change in y. So, change in the linear approximation. And so the change in y, the change in the function, that's not perfect, but it's our approximation. It has to be about 0.136. Okay, so just to reiterate, I think it's important that you have a basic understanding of how this works, how it kind of ties into the linear approximation. But really the key thing is to be aware of this relationship. You're going to start to see some dx's when we're working with integrals and antiderivatives at the end of chapter 4 and into chapter 5. So just be aware that there's a relationship here outside of just matching notation. All right, so that's it for section 4.6. Let me know if you have any questions.